Hi. I'm going to lecture in English. I hope people realize that. This is the first time I've ever talked to a book festival. And I think somebody has trouble counting because I have 3 instruments and 2 hands. So you'll see me fumble around. Anyway, the picture here I picked is not science on this side. It's actually the closest I've come to recently talking to a book festival was an art festival, and it was in Vienna. And this is an artist named Harold Rich's vision of what gravitational waves are. So it's not this, you'll see if it matches anything I say, but anyway, it's his view of what gravitational waves are. I'm going to give you kind of a story view of what we know about gravity and why gravitational waves have ever come about and been discovered in a kind of story form, but it's not fiction. So, we'll start with something that hopefully everybody in this room saw when they were pretty young, and that is at school your teachers taught you about gravity, and they taught you that this guy here, Sir Isaac Newton, told you what happens when an apple falls from a tree, or the moon going around the earth, or the earth around the sun. He developed, I have a formula here, but don't be intimidated. It's the one formula that probably you saw in school, and it was the formula that Newton wrote in the Principia in 1687. That book was famous for 2 reasons. One is that Newton wrote down the scientific method in that book, and of course that's what guided us to do science. It's something I wish people paid more attention to and probably could sort out the difference between real truths and false truths that we're having trouble with, at least in my country right now, of whether what we're told is right or wrong. Certainly using the scientific method, we have a pretty good way of sorting that out. As an example of the problem in my country, before I get into this, global warming, that's a scientific question. As a scientist, I know how to look at what the evidence is, but I'm afraid in my country it depends on which political party you're in, whether you think global warming is real or not real, which is a problem of society, I'm afraid. Anyway, I'm supposed to give a physics lecture, so I'll go on with physics. In 1687, Newton told us that if we have 2 bodies, it can be the earth and the apple, it could be the moon and the earth, it could be the earth and the sun. They pull on each other or attract each other with this formula here, that it's the product of what the 2 masses, inversely proportional to the square of how far apart they are, and with some constant that tells you the strength. It actually, he didn't know the strength, so he just called it G. And it took another 100 years for somebody to figure that out, but it's a different story than I'll tell tonight. So that's the formula. That's what Newton did. And it simply is the most successful formula, the most successful theory ever in physics. So if you know that's one thing that Newton did, it's basically the most successful theory ever in physics. Yet, I'm going to spend the rest of the lecture telling you that we've gone beyond that formula. That doesn't make that wrong. It's the way science develops. Newton wasn't wrong. His theory, as I'll show you, was incomplete. And so somebody else came along. It was Albert Einstein, who taught us or developed a new theory of gravity more than 200 years after this one. And I'll show you the only things that weren't right about this one as we go along. So, what happened is that this guy, who's a Frenchman, and he was named Urbain Le Verrier, he was a mathematician and is often referred to as the father of celestial mechanics, which means that he learned how to calculate where all the planets were and so forth in detail and explained it to us in the 1800s. And he noticed in the 1800s, remember Newton wrote this formula down in the 1680s. Nothing had been seen that might deviate from it in 150 years. And then this scientist came along and noticed a discrepancy. And what he noticed was that the orbit of the planet Uranus around the sun didn't quite fit the formulas of Newton and Kepler. Kind of what we learn in school is what makes the planets go around. But because Newton was so much the idol that he couldn't possibly be wrong, he did more or less the reverse engineering of looking at how Newton could be right, and yet what he saw was wrong, what looked wrong. And so that was that maybe there was a planet that we hadn't yet seen. And so the orbit of Uranus was somewhat distorted by a planet we hadn't seen. So he calculated what this planet would be if it was there. And he even named it. He gave it the name Neptune, so you know it's real because we know we have a planet Neptune. He wrote a letter from Paris to Berlin to an astronomer in Berlin. He gave it 5 days to get to Berlin, and told the astronomer where to look up in the sky. And within 1 degree of where he told him to look, he saw the planet Neptune, and that was the discovery of Neptune. So Newton's formulas still were fine. Not quite the end of the story. And that's what I tell you here. Then he noticed a little bit later, he's famous now because he's the one that brought us the planet Neptune. But he noticed that the orbit of Mercury, that's our planet that's closest to the sun, and it's very elliptical, long orbit it comes around, and it makes kind of a daisy pattern. And he noticed that that daisy pattern, when it comes around, didn't quite satisfy Newton's equations. And if I can manipulate the third arm here. And he saw not a big discrepancy, maybe 10%, but that the orbit of Mercury, which is our planet closest to the sun, when it goes around, didn't quite come back to where you'd calculate it would be. Of course, most scientists would again think that there's something missing that we hadn't seen, but he actually then did that, and just like he did for Neptune, and he predicted that there was some missing planet or masses between Mercury and the sun. And a lot of scientists looked for that in the 1800s. This is now 200 years after Newton's theory. They looked for that in the 1800s, and a few people claimed to discover some new planet. They were wrong. I mean, other people disproved them. So this was still a puzzle by the time Einstein came along. So what I've been trying to set for you is the scene by the time Einstein came along. The only discrepancy in 250 years almost after Newton about gravity that was real, where it didn't predict something correctly, was this. And yet we didn't know yet whether there was something between Mercury and the sun. So it hardly was the stimulus for Einstein to make a whole new theory of gravity. In fact, after Einstein's theory, which I'll come to next, after Einstein's theory, NASA spent a lot of money looking for objects between Mercury and the sun. They didn't find any. So it was still an open question after Einstein came along. So that was the only discrepancy, and usually something physical is what we do. I'm not putting this formula up to scare you away, just to show you that there is a formula like the one you saw in elementary school that Einstein would write down to describe gravity. It's a little bit more complicated, and we're not going to talk about it at all. I just put it down for symbolic reasons. And Einstein, what he did is that he basically decided that the way we treat space and time is separate. Time is a very complicated subject, as people probably know. And so he made space and time come together in a common theory. I'm not going to show you the theory very much. And so space and time are now together, and it forms one word, space-time. Bill Gates doesn't yet understand that, so when I type it in Microsoft Word, I get a little wavy line underneath. But in Einstein's theory, that's the basis of the theory, that you basically put it all together. And the words that you hear, if you've never seen anything other than now I've described it scientifically, is you hear in science fiction the warpage of space-time, those kind of words. That's basically telling you that space and time got integrated together. And as I'll describe it physically, you'll see what I mean by that. So this is what Einstein did technically, and it solved this problem. He got the right answer, which was 10% different. So that's a small success. In physics, we very rarely accept a new theory of physics because somebody explained one deviation in some other theory, and especially in the most successful theory of all time. So this is not the reason why we take Einstein seriously, but at least I have to record that he did get the right answer for Mercury around the sun, and there was a good reason why Newton didn't get the right answer for Mercury around the sun, which is part of why there's more to the story that Newton's theory didn't explain, and Einstein does by putting space and time together. So let's look at what it means to put space and time together. If we put space and time together, imagine this picture here, which is a picture of a coordinate system for me. For you, think of a trampoline. So if I take a trampoline and I put a big mass on the middle, it distorts it in the picture that you see here. And if it distorts it, if I don't have a trampoline on it and I put another body on it, it just sits. But now if I put something else, it'll roll toward the central body. That's the apple rolling toward the tree, toward the earth, basically. The earth, so Einstein, by having a distortion of space-time, which I've pictured here in 2 dimensions, it happens in space and time, 4 dimensions, which I can't draw, then that explains something that Newton didn't. Because even though Newton was so successful, and you all learned when you jumped up, your teacher told you the earth pulled you down, I bet very few of you asked your teacher why the earth pulled you down, because Newton didn't explain that. And it's kind of embarrassing, because kids are curious why you didn't ask, but I bet there aren't very many people here that didn't. I didn't ask when I was a kid either. So that's why the earth pulls you down. It's the distortion of space and time, and that's already now gone one step beyond Newton. Newton recognized that he didn't explain why gravity works. He just gave you a formula that described gravity and how it works. And in fact, again, in the period in between Newton and Einstein, people tried to explain why the apple falls to the earth or why the earth goes around, but it was usually completely wrong. It had to do with electricity and magnetism. So nobody had anything but a good idea until Einstein came along. And so this describes why the apple falls to the earth. The second problem so that's one problem with Newton's theory. So now Einstein has fixed 2 things. One is the Mercury around the sun. And secondly, he answers the question of why these objects pull on each other, and not just that Newton's equation is there. The lights have gone off as I'm going to talk about light. So the second problem, and actually Newton recognized this, is that in Newton's theory, when the apple falls, you know it immediately. Okay? And so there's no time between when the apple falls and when you see it. But in real science, where we have objects that are far away, we don't necessarily know right away. So imagine that this is a picture of the sun and the earth. Imagine that the sun disappeared right now. Somehow it exploded and disappeared. It would take 8 minutes for us to know that, because that's how long it takes light to come from the sun to us. Since it takes 8 minutes, what about the gravity that's pulling between the earth and the sun? it also would take 8 minutes. And so in Einstein's theory, gravity also travels at some finite speed. We call it finite speed of information flow. That is not infinite. When I talk to you, it doesn't get to you right away. So that, again, in Einstein's theory, there's only one speed. We call it the speed of light. It's very fast, but it still takes 8 minutes from the sun. Much more from objects that are further away, and this is what stimulated Einstein's theory. And when I talk about gravitational waves, I'm going to talk about objects that are 1 billion light years away, so a long, long ways. So anyway, Einstein then basically added the fact or explained the finite speed of information travel, or information transport. So he solved the one problem, which is Mercury, and two conceptual problems that Newton did. And I want to emphasize that doesn't make Newton wrong. It's the way science evolves. So sometimes we do things that are wrong. Usually we do things that are right, but not the whole story. And something new basically adds to the story and maybe changes it a little bit. But nothing fundamental that Newton did was wrong. He just didn't explain finite speed of information travel. He didn't explain why the apple falls. And for some physical phenomenon, and the one of Mercury going around the sun has enough of some of the concepts of space-time coming together that Einstein has that makes Newton's calculation a little bit wrong. So let's go on from that. Today's scientific discoveries often become then a tool for science in the future. So I've talked about curvature of space-time, and in Einstein's case, he made a prediction, and that is that he now gave you a better theory of gravity, but so what? Well, that doesn't make us accept something that was more than 200 years in the making. What it should do is predict something new that Newton didn't predict, rather than just what if the sun burned out or something. And so what he did, and this is in 1915, when he brought his theory out, is he predicted that light, if it was near a massive object, would bend. Why? Because around that massive object, we've distorted space and time, so it'll bend as it goes near it. He not only did that, he calculated in detail how much it would bend if a star behind the sun went behind the sun and the light, you were watching the light. The only time you can really watch the light is if there's a full eclipse, when the sun is black. So he made the prediction that if you looked at an eclipse of the sun and watched stars go behind it, that you could see this bending. And that was done in 1919 by Arthur Eddington, who then became Sir Arthur Eddington as a result, and Einstein's theory was right. So this was a strange phenomenon. It was very well known. It is what made Einstein a household name, actually. It wasn't E equals MC squared or something that you might have heard of, but what captured the imagination of people around the world was light bending. And then Einstein became kind of a folk hero. This is just a picture of the concept that that's a full eclipse of the sun. Because of the distortion of space, when you get near it, shown on the left, that light will bend a little bit and you will see it differently than a straight line. This is the headline that was in the New York Times when that experiment was done, and you can see that they thought it was all, whoever the reporter was, thought it was a little crazy. The fact that light would bend and so forth, as you can see in the headline. Okay, so the next thing is another way that science develops. That is, you learn something new, light bends, fine, it even bend around the sun, and now it can become a tool. And it's a common tool in astronomy to do the picture that I show here, and that is to look at a source when something's in front of it and see what happened to the light that came from it and that it bent. We call it gravitational lensing. So the object in front, which we don't care about, is bending the light, and we can tell something about the object behind it. This is a picture of light going around an object, and the bottom one is one that you can see with your naked eye. On a really good day in the southern hemisphere, it's called the Einstein cross, and those little dots that you see around it are light bending around the object. So it's a common tool and a common observation in astronomy now to see bending of light around some object. Okay, the next thing before I go on to gravitational waves is that I'm talking about this really obscure theory of Einstein's space-time. I wrote down a formula that probably no one in the room understands from Einstein. But did you know that you use general relativity, Einstein's theory, probably almost every day of your life? Because GPS, which is guiding your car, and you when you walk, wouldn't work without making a correction for general relativity. So what happens is that GPS works by having 24 satellites that are going around, and we measure the amount of time it takes for a signal to go back and forth from the person walking here or driving their car and the number of satellites that they happen to see, 4 or 6 during that period of time. And it turns out that the satellites are up very high and they're moving fast. And because they're moving fast, they basically are what we call relativistic. And by being relativistic, it means that what we learn when we study physics is that moving clocks tick more slowly. You've, of course, heard that in science fiction because they send somebody off in a spaceship and they don't get old as fast as the person on the Earth, and that's the same. That's not made up by the science fiction writer. It's Einstein's theory. So moving clocks move more slowly. Because of that, you have to make a correction in the satellite, which is made, for the fact that the clock is going to tick more slowly than you think it is, and yet you're going to compare these. That's not the end of the story, because that's Einstein's first theory called special relativity that he gave in 1905. The second, which is what I'm talking about today, which is the gravitational one, or general relativity, is gravity. And that has an effect too, because the satellites are high enough so that the gravity that they feel is only about a quarter of what it is on the Earth. The fact that it's only a quarter means that the effects of how much space and time are distorted around it are different. And so there's a correction for that too. That correction is bigger than the other one and the opposite sign. It's 45 microseconds per day. Those numbers don't mean much to you, but if I put the numbers in, which I'll do for you, first you add them together, the total correction is 38 microseconds per day. What does that translate to in terms of keeping you on the road? If we did not make the correction, then I do it for you here, but I'll just tell you, then it would take about 2 minutes and you'd be off the road. So basically, GPS only works because of Einstein's general relativity. You can imagine that it was hard to convince the US Air Force, when they made the first satellites in the GPS system, to make a correction for general relativity, because there's probably no one in the Air Force that understands general relativity, but they finally did make this correction. So that's the background. Okay, with all of that in mind, Einstein made one more prediction, and that's the one we're going to talk about the rest of the lecture. And that is that in 1916, 1 year after he introduced this new theory of gravity, he wrote another paper. The front of that paper is shown here. And in that paper, he basically made the hypothesis that gravity would have what I'm calling gravitational waves, or what we'll talk about the rest of the lecture, gravitational waves. And that came from the fact that when he looked at the equations of general relativity that he had just developed and put them in a certain form, except for the letters being different, it looked a lot like the equations of electricity and magnetism. And we know that electricity we have, the lights, we have magnetism, we have magnets, but we also have electromagnetic waves, the light that comes to us, and electromagnetic waves, microwaves, and so forth. And so if the equations look the same, being Einstein, he didn't develop it from first principles, he made the leap that if the equations look similar, there's probably waves to do with gravity as well. And so he made that prediction in a little paper in 1916. The paper was full of errors, actually. And he wrote a second paper in 1918 where he corrected the errors. He never admitted there were any errors, he just moved on. And he wrote a paper in 1918 where he described what the source would be of gravitational waves. So I'll remind you that in electromagnetic waves, the simple way you make an electromagnetic wave is take two charges and you go like this. And that makes an electromagnetic wave. Charges, not my fingers. So they'll make electromagnetic waves. But for gravitational waves, they're a different form, and it takes 4 instead of 2. And so it's called a quadrupole, and we needed that to know how to go look for them. So he gave us how they would be made, and that was the source of gravitational waves. He also made an offhand remark that the effect, even though he considered it to be real, would be too small to be measurable. And that, people make a big deal that Einstein didn't think they would ever be seen, but you have to put it in the perspective of somebody in 1916 or 18 not knowing about modern lasers and interferometers and so forth that we use in the measurement. So, Einstein then tried to develop gravitational waves as a good physicist would from first principles instead of from an analogy to electromagnetism. He did that in 1936. He tried to write an article where he put doubt in the mind. He called it "Do Gravitational Waves Exist?" A funny name for an article when he's already written one 20 years before saying that they do exist. So he's obviously questioning it. And he submitted this article to our most prestigious journal, called Physical Review, and it went out for peer review, which was only being introduced at that time. This is the 1930s. And it went to this man here, John Tate, who was the editor of the journal. And John Tate had the choice at that point of accepting any article that was put in for publication, rejecting it on his own as the editor, or sending it to some expert anonymously to review it. And this is the logbook everybody wrote in longhand then from the articles submitted to the journal, and there's 3 of them there, or 4 of them. The second one is Einstein and Rosen, and one of the articles he accepts, one of them he just rejects, and that one he sent out for review. So he sent it out for review, and that was reviewed by a physicist that wrote back and said that Einstein had overlooked really how to put it all together and suggested how it should be. Tate, the editor, sent the article back to Einstein. I think I had it on here with a very mild letter that said he'd be glad to have Einstein's reaction to the referee's comments. Of course, Einstein's reaction was that. And Einstein basically then rejected, wrote a letter which was not as mild as the letter sent to him, saying that he had sent the article in to be published, not to be sent to some reviewer who was clearly falsely looking at the information anyway. And so he withdrew the article. And in fact, that article he published in a different journal named after Benjamin Franklin at the Franklin Institute in Philadelphia. That journal doesn't exist anymore, but existed at that time. This is the letter where he wrote back and said he was pulling it. So basically, that's what happened. I'm saying all this to partially tell you there was a lot of confusion about whether gravitational waves exist, whether they could be detected for a long time before we came along. So the person who was his assistant at that time was a rather famous astrophysicist named Infeld. And Infeld had a meeting with the person who reviewed it, even though they didn't tell him that he had reviewed it. When he was reviewing it, he was at my institution in California on sabbatical, and then when he came back to Princeton, And Infeld talked to Einstein about it, and they changed the article. As you can see, it doesn't say, do gravitational waves exist? It says instead, on gravitational waves. And he tries to derive it. Not a very good job of deriving it, actually. So it didn't convince the theoretical community yet, beyond Einstein, that gravitational waves should exist. That took another 20 years after Einstein was dead. And mostly people attribute it to this meeting here that I reference, which is a meeting in the 1950s. So we're already 40 years after Einstein had predicted gravitational waves, and they were still debating whether they exist. At this meeting, a British physicist named Pirani actually did a very beautiful derivation, as physicists like to see, from first principles from general relativity of gravitational waves. Secondly, at that meeting was Richard Feynman, a colleague of mine at Caltech, and he was a very kind of physical physicist, and he suggested that if gravitational waves exist, then they have to be able to transfer energy. If they can't transfer energy, it's just a concept. So he made what we call a Gedanken experiment, a head experiment that you can think about, which is a bar. If I have a bar and I put a couple rings around it, then when a gravitational wave comes through, it expands the bar a little bit. That creates friction with the little rings. They move, and that makes heat, and that's a transfer of energy. So the combination of the physical explanation of Feynman and the proof of Pirani made people believe in gravitational waves. From that time on, it became a very difficult experimental problem to try to detect if they exist. And that's what I'll come to next. So the reason they're so difficult to detect is that despite the fact that we have this great theory that distorts space and time, we're really lucky because the parameters of the world we live in, the universe we live in, are such that if you want to think about space, what does it mean to distort space? If you think about it like a material, we have materials like a rubber band that bend easily, so they're easy to distort, or a piece of steel that's hard to bend. Space has the parameters, if you want, of being very, very stiff. So we're lucky we live in a world where we don't see much of this. We really have to do exotic astronomy or something to be able to see this kind of effect. It doesn't happen that when I look at you, light's bending and so forth, so you look fuzzy. Anyway, so the amount is very small, and the amount I illustrate here. If I had a circle, and in that circle I had little free masses that could move, and a gravitational wave goes through it, what's it going to do? It's going to distort it like this picture here. It's going to make it look like an ellipse instead of a circle. But the amount that it distorts it is only 1 part in 10 to the 21 for the kind of source that I'm going to show you we detected. That's a really small number. That's 21 zeros and a 1. So that's the size. If that circle was 1 meter in size. So to make the problem a little easier, we make our detector a kilometer in size, which makes the problem 10 to the minus 18 instead of 10 to the minus 21. So now let's look at what happens. Einstein told us the way gravitational waves are made. If we have two objects and they're going around each other, like the Earth around the sun, or in my case it's going to be two black holes going around each other, then they're going to, by Einstein's theory, they accelerate by going around each other, and they're going to radiate away, shown by the waves here, gravitational radiation, or gravitational waves. Because they radiate away energy, they slowly in-spiral toward each other and eventually crash together. The biggest signal, as you can imagine, is when they crash together. So what we did is make an experiment to look at this last part where they come together and they crash toward each other so we could detect it. So this is a picture. Two black holes going around each other, giving the waves that go out, and now we're going to detect it, and the amount is this small number, 10 to the minus 21. So I'm just going to work with small numbers for just a minute so you can understand how hard the problem is after I show this. The technique that we use is a technique that's very good at seeing small effects, and that is called interferometry. So what you're seeing here is light coming in, splitting in two directions. If the two lengths are the same, it'll take the same length of time to go down one and come back as it does the other one, and they'll come back and exactly cancel each other, which is shown here. One's going up and the other one's going down. But if one of the arms gets a little longer than the other or shorter, then they won't quite cancel, and you see something in this detector on the right. That's the principle that we use. It's called interferometry. So how well do we have to do it? And this is the two numbers that I'll give you. We use a light, like this laser beam that I'm holding here, and the light beam itself has a wavelength. We have to be able to tell a shift in the distance that's 1 part in 10 to the 12th, the wavelength of the laser beam. So that's a very tiny number. The second is that we're here on Earth trying to do this experiment, and despite the fact that it seems pretty stable, it's moving around a lot, and we couldn't possibly do the experiment without isolating ourselves from the Earth. It's hard to isolate. You try to float, but you can't float quite, so you have to make fancy devices to keep yourself off the Earth, and we have to do that to 1 part in 10 to the 12th also. So those are the two magic numbers that we have to do. The second one was the one that we finally solved when we saw gravitational waves. These are the two detectors that we have. They're just physical pictures of what I showed you for the light going back and forth. They're 4 kilometers on a side. The right one is in Livingston, Louisiana, and the left one in Hanford, Washington. They're 3,000 kilometers apart. And you'll notice in the right one there's water going down the side. Louisiana is very swampy, and basically a millimeter below the surface is water. So we built up a berm to put the detector on, and it immediately made in the pit where we got the dirt, filled up with water, then fish, then bugs, then alligators, and so forth and so on. So basically, that's what we have. And those are our two detectors. This is just to show you that there's real apparatus. That's a mirror on the right. And on the left is just a picture of the round trip, which I'm going to skip. So, again, trying to do that. Okay. So, this is a picture. I'm going to show you what happens. This is a picture of 2 black holes drawn by a computer from the data that we have. The surrounding is the fact that it's in the universe, very far away. And we're going to watch what happens to that in the film. This is 1.3 billion years ago, what I'm going to show you. Or what that means is that's when it happened. It's taken 1.3 billion years for the signal to get to the Earth. Sounds unbelievable, but true. So what's happening is these 2 objects are going around each other. They're what we call black holes. What's a black hole? So let me remind you or tell you what a black hole is. Remember that I told you that Einstein said that light will bend. So anything can bend. If I make the gravitational field strong enough, I can bend light so much that it can't even get away. It'll bend back to myself. So if I make gravity really strong enough, nothing can get out. That's what we call a black hole. That happens if a star burns up all its fuel and collapses, something we call a supernova. If the star is big enough, our star, our sun, isn't big enough. It won't make a black hole. Sorry. But if we have a star that's 3 times our sun or more, we think that it's big enough to do that. So there are stars that are bigger, and two of those might go around each other, just like the Earth around the sun, and that's what we're looking for. So that's basically the concept. This is from the data that we took. I'll show you the experimental data in a minute. So the 2 black holes are going around each other, and then we've redrawn it as a computer from the computer imaging of what it looks like. As they go around each other, they're distorting all the galaxies and so forth near them. As they come to each other, they finally eat each other up, and then you have one object that's heavier. That's what we saw. So how do we see that? First, when they're coming together, how far apart were they and how fast were they going? This is where you basically stop believing me. If I draw a map here of Pisa and Florence, these two black holes, when I'm going to show you the data, are only apart by about the distance from Pisa to Florence. They're going around each other at about half the speed of light. And they basically are each 10 million times the mass of the Earth. So we have these two objects about the size there that are so compact, they're 10 million times the object. Then as they crash together, they make this gravitational radiation, which took 1.3 billion years to pass through. It comes to the Earth. This is exaggerated just a little bit. And because they distort space-time, they distort the Earth, of course. Actually, the amount they distort the Earth is a little less than this, and so we have to have a special detector to see it, and that's the picture that I showed you of our detector. So we built these detectors to be sensitive. I'm not going to be any more technical, but on September 14th, 2015, not so long ago, this black hole, the signal from the gravitational waves came up through the southern hemisphere. And we know it from our own detection that it came through this little banana-shaped area early in the morning for us. And then 20 milliseconds later, it had come through the Earth and gone through our detector in Livingston, Louisiana, the one that I showed you. And it made this picture here. This picture here, from left to right, is about 0.2 of 1 second. Up and down is the size of the signal, and you'll notice the scale is 10 to the minus 21, the units that I gave you. And you'll see the wiggles. The wiggles that are going up and down get bigger and narrower, and then they come together and make the final one, and then a little wiggling at the end. That's kind of the picture that I showed you. They're going around faster and faster as they're coming together. When they merge together finally, that's the biggest signal, and then there was a little bit of settling down that you might have noticed. That's the wiggling at the end. 7 milliseconds later, that's not very long later, we saw a signal that looked almost the same. They look different color on here, but they're pretty much the same in Hanford, Washington. This is basically raw data. It's almost never in physics that we get something that looks like this and it's a discovery. Usually we have to go through an enormous amount of computing and all kinds of things, and then we show you something that's beautiful, but it didn't look like that at the beginning. This was so spectacular that we knew what we had essentially immediately if we didn't make a mistake somewhere, which we had to check. So we saw these two, and then I've drawn a line through them. You can barely see the line. I'll take it away and put it in. That line is the calculation of Einstein if two black holes were merging. So you can see how well the data is more jagged because we can't make the apparatus noise-free. So this is then the result. That's the picture of what happened. They're further away. They're a little wider. As they come together, they're bigger and narrower. They merge together. And while they're doing that, if you look on the bottom, it shows velocity on the left side. We're going from about 1/3 to 6/10 the speed of light. So they're very, very relativistic, which is what I showed you in the picture. So that was the discovery of gravitational waves, which was in 2015. And then we saw it in 2015. In 2017, we went to Sweden. So that was good. 2 weeks after that, we showed this event here. And this event here is totally different. What it is a different kind of collision. It's a collision of something we call neutron stars. What is a neutron star? I mentioned that our sun, when it collapses, won't have enough gravitational strength to be a black hole. it might be a neutron star instead. So neutron stars are very, very compact nuclear material. So it acts for a physicist, very different. We have nuclear material in one case. In the other case, we have a hole that doesn't have anything we can see, even though they weigh something. And so we saw that, and it happened, which you have to believe me, from the very top, luckily, at almost the same time that an astronomical instrument that was flying was looking for something we call gamma ray bursts. And they happened to be looking in the same part of the sky and saw a signal 2 seconds later. 2 seconds later, the signal that we saw, we can tell by the size how far away it was 100 million light years. So the first thing is, if we were seeing the same thing, we know to an accuracy of 2 seconds out of 100 million light years that gravity travels at the same speed as light, one of Einstein's predictions. Putting that together, the fact that they saw something and we saw something, which wasn't possible with black holes because they don't emit anything anybody else can see, we alerted the whole astronomical community, and all these lines, which I'm not going to explain, are all the different wavelengths going from X-rays, infrared, radio, ultraviolet, and so forth. And from that whole picture, we got a picture of something that is given a name. We don't care about the name, but it's called a kilonova, which is a description of the nuclear physics when these two objects come together. It turns out that although it's kind of serendipity, it isn't what we do and what we're looking for in science, we probably learned something new that you can relate to. And that is that it's been a puzzle for physicists, as long as I've been a physicist, and probably longer, that where the heavy elements came from in the Earth. How did they get in the Earth when the Earth was formed? Where did the elements come from anyway? We know the universe is made essentially out of hydrogen and helium. That's what's out there. And then you have stars that are burning, and they burn by what we call a fusion process. And the fusion process starts by, just like hydrogen bombs, but it's not a bomb, it's controlled. The fusion process starts with the light elements, hydrogen and helium, and goes up to lithium, oxygen, and burns. And eventually, as I'm sure all of you know, a star, including our own, will burn up all its fuel. At that point, the outward force from the fusion process no longer is compensate for gravity trying to pull it in. It collapses. That's called a supernova, and there's a big flash in the sky somewhere. So basically, that describes where the elements came from, supernova, star's lifetime, up to about iron, because fusion doesn't work for heavier elements than iron. Physicists think they have to be able to explain everything in nature anyway, even if it's wrong. And so we made up a theory, which was never very satisfying, to describe where the heavy elements came from. And that was that there was some special process, we call it the R process, it doesn't mean anything, that describes that there was some enhanced process in the fusion process in the sun and stars that would make the heavy elements. It was just a way to try to explain things. Now, we think we have another explanation. We're not sure because we've only seen one example of these neutron-star collisions, but it turns out that in the picture here, probably your favorite heavy elements, platinum and gold that are on your fingers and you like to wear around, didn't come from this theory that physicists would have told you 2 or 3 years ago, and that is that it came from stars somehow having a special process. But at some earlier time, something like we just observed, the collision of neutron stars. It's probably right, I think, because if you ask me, how do we know all these elements that are down in the bottom of this chart, and you read about every once in a while in a newspaper that somebody found a new one and it gets a little longer. What is done generally is to take some heavy element, a lot of neutrons, bombard it with neutrons, and then you make a heavier one, and then you get famous and name it and put it on the chart. And that's more or less a simplified picture of how the heavy elements were found artificially, meaning created in the lab. So what can simulate that better, when I said neutrons, than having two neutron stars that are colliding? So the neutron stars, when they collide, make a lot of gold. If you calculate how much gold was made in the one that we observed, it's pretty impressive. In the observation of the neutron star, about 100 Earth masses of gold were created. Of course, that neutron star collision happened now, so it doesn't describe what's in the Earth, but an earlier one would have. Okay, just a little bit about the future. So you know this isn't the end of the story, it's the beginning, I think, or near the beginning. This science will be pursued first by us on Earth, like we're doing now, and what you see on the right is us, LIGO or Virgo here in Italy, we become more and more sensitive because we're not limited by nature yet. We're limited by our own ability to make instruments that are sensitive enough. So we know how to make better instruments, and that'll happen in the coming years. As we get more sensitive, we can see further out, we can see more things, and that's LIGO. There's also a project in space called LISA, and that looks at a different frequency. And the reason that's interesting is just like in astronomy. In astronomy, much of what we've learned in the last 50 years or so is looking at the same phenomenon, but looking at it in different frequencies, different wavelengths. For example, you look at the same object in the radio and the X-rays and the visible, infrared, ultraviolet, and you put all that together and then understand the science of what's happening. So in gravitational waves, it'll be similar. We want to study all the different frequencies or different wavelengths to understand the phenomenon. At yet lower frequencies, lower showing on here, is using a technique which does very accurate timing using the fact that we have pulsars that are very accurate clocks. If we look at a lot of them simultaneously with enough accuracy and a gravitational wave goes through, it changes the timing and you might be able to detect it. That may be the next kind of detection that's made, in my view, of gravitational waves. So this is the one in space. It's 3 satellites separated by 2.5 million kilometers, and it's supported by the European Space Agency, and it's scheduled to fly in the early 2030s. So some of you may know in advance and watch for it. They've done the technology test of knowing whether they can put something in the satellite that's sensitive enough, and that was very successful. So now it's just the engineering and getting the equipment together and on a schedule where they can get this complicated orbit up and so forth. This is the pulsar timing array. The last thing, which I'll comment on and then I'm done, so wearing you out, is my own personal view of where the ultimate new knowledge that we really all maybe care about will happen. And it's not now, and I don't know how to do it yet, but the ingredients are there for gravitational waves, and that is we all wonder how it all began. We hear this thing about a Big Bang, but what do we know about the Big Bang? What do we know about how things started? There's a big puzzle, bigger than the one that I talked about for where gold and platinum comes from, and that is even why we're here, all of us. We know when we go in the laboratory, we make an equal number of particles and antiparticles when we use energy and make mass. In the early universe then, when we had a lot of energy in the Big Bang, it should have made, by everything we know, an equal amount of matter and antimatter. Matter and antimatter would annihilate each other, and we wouldn't be here. So somehow, there's something we don't understand yet, and that is there was a small asymmetry at the beginning so that matter and antimatter annihilated, but there was some matter left over that ends up being us now. But we don't understand how or why yet. Why is it so hard to know why? It's because we can't really go back in time to the Big Bang very easily. The way we do that is to look further and further out to the edge of the universe. We can't do that with our best tool, which is photons, telescopes, and so forth, because the photons from the very early universe all got absorbed. So we can go back to 400,000 years after the Big Bang. Everything we say happened before that is in physicists' minds a little bit like the reason you have gold and platinum. We make up that from clues. Gravitational waves are the one source that we have that wouldn't get absorbed at all. So if we can make instruments that can go back to the very early times or out to the edge of the universe, and I think that looks like it's possible, not today, but in the future, then we can actually start to see real information for what happened in the early universe and hopefully solve a puzzle like why we're here. With that, I'll quit. Thank you.